this video, we'll be taking a close look at a fully operational Bombenzeilanlage, or bomb target system known as the BZA, or Bomb Zeil Automat, automatic bomb line in English, and the Stuvi 5B optical sight. The BZA was an analog computer system designed to process a range of critical aircraft sensor and pilot inputs to calculate the precise bomb release point, typically for aircraft like the JU88 and the Arado Ar234 executing dive bomb attacks. The BZA computer was able to process moment-to-moment critical aircraft data, including altitude, speed, wind, track, and dive angle, as well as target data related to position and geo-altitude. The information was updated in real time and presented in a simple active terrain overlay reticule of the Stuvi dive bomb sight. Here's Dieter Beikirch to tell you more.
What the bombing man see, he sees the target, yeah, maybe the factory or so as a target, and here is the mark. The mark is moving. He sees the target, and here is the mark, and when it is so that the target and the mark is together, then is the correct position, and he has to press the bomb knob. So, yeah, and here, what you see here, this is only a vizier for the normally weapons, yeah, machine guns and so. This has nothing to do with the bombing system. This here, this is for the normal weapons. I have told on the picture that the aircraft comes and goes so down and let fall the bomb. But to have the right position, he has to look in this glass. He sees the target, and also in the glass you see a mark. And when the mark is over the target, then he has to press and leave the bomb. Yeah? So, but when the aircraft flies, it has speed. We have wind from right and left. We have different air pressure and so on. And all these parameters was calculated by this computer. This is a electromechanic computer. Yeah, you see here when you see these are working here. Yeah. And all this movement from the aircraft changes the dot was here going. Also the speed or the height. Now we are 2 kilometers up. Yeah. Oh, here's the speed. Yeah. So these parameters depend on the correct point of target. Yeah. So, and what I can show you, he has to look here inside, and there is a point, and this point has to stay over the target, and then you can press. Yeah. This is a function of this very difficult system. Yeah. I can show something. Here you see the motors give the position to this point. Yeah. Straight. Yeah. And here speed. Yeah? And how it's done? This is the electric system. Yeah? The same movement makes this. This was also in Fourier 10 the same. Yeah? I move here, and for the computer, this here moves here.
It's worth pausing for a moment to consider the remote control technology that Dieter is referring to here, as it's not very visible today. It's the system that allowed the Stuvi's dive attitude and bomb release computer to be constantly updated by automatic flight sensors and manual pilot input, and for the computer to instantly update the Stuvi's cockpit optical sight. Many military and industrial control systems used the same technique from the 1930s to the 1960s, but it's rarely seen today. Called Synchro control transmitters and receivers, the system is sometimes referred to by its once popular name Selsyn, a shortened version of self-synchronizing. This device is a synchro receiver, one end of a system used to transmit an angular position from one location to another. You can see that the devices, especially the smaller ones, look just like ordinary electric motors, and mechanical connections for gear trains and drive shafts can be attached to the rotor spindle in the same manner as motors. But in fact, they're not motors at all. Synchro units are transformers. Synchros typically have 5 cables, 2 for power and 3 to control the rotor position. In a synchro system, the transmitter windings and the receiver windings can be thought of as the primary and secondary windings of a transformer. The voltage induced in the receiver windings is proportional to the angle of rotation of the transmitter shaft, and the receiver rotates to the same angle as the transmitter as a result of the induced voltage. Here's a little model we've made. You can imagine it's the gun turret on the deck of a ship that has to communicate with the fire control officer in the plotting room. Typically, a basic system like this consists of a transmitter and a receiver, both of which contain a set of 3-phase windings. The transmitter is connected to a shaft or other rotating device, in our case a bearing needle, and the receiver, here connected to a gun turret, can be at a remote location that can be anything from a few inches, as here, to a few miles in the case of a real coastal gun battery. Let's connect this up now. Plug it in. Make sure we're switched to AC. If I get the polarity wrong, it won't blow up. It'll just point with a 180-degree error. Switch on and set the output to 25 volts. I can move this bearing needle, and wherever I point, the gun dutifully follows, matching the movements perfectly. Wherever the needle points, the gun points in precisely the same direction, and, with some upper speed limitations, it moves quickly or slowly as I choose. And as you can see, it works just as well with the gun acting as the transmitter. Invented in the 1920s, one of the most famous early uses of synchro technology was remote monitoring and controlling of the sluice gates and valves along the Panama Canal, sometimes over very long distances. One notable feature of synchro units is their resolution. In the split-screen demo here, even the smallest movements I make have surprisingly precise corresponding movements resolved on the remote device. Another useful feature is that they're self-synchronizing, without any calibration or additional adjustment. If I cut the power and adjust one unit so that it's out of phase and synchronization with the other, as soon as I restore power, they instantly return to synchronization. And it works just as well the other way round. And this is all done without control boards, firmware, chips, logic boards, you name it. Just the laws of Faraday, Lentz and Ohm. It's precise, fast and tough technology, very difficult to defeat. You have to penetrate deeply into a weapon system that uses it. James Bond isn't going to twiddle something on his watch to change this control system.
Now I start this test system. Yeah. And I have to put into the calculator some parameters. Yeah. For example, Now it's ready, really ready. I have to put in the calculator some parameters. Wind change. You see the air pressure, millibar, and the altitude directly over the target. I have to that is the altitude from barometer, altitude meter. I have to put inside the speed. So, and I have to show you the angel. Here you can see. Again. And also speed.
What is this one, Dieter? What is that one? That seems to be changing with the angle. That seems to change with the angle.
Yeah, this is angel. This is the angel.
And the one at the back.
And this one is the Visierwinkel. Like the same with the angel. The Visierwinkel. This is it.
The visor angle. The visor being the bomb sight. So this will be the control angle for the mark, the pipper.
Here you can see the altitude. Yeah.
We're going to show you a quick computer animation to give you a better idea of what the system may have looked like in use. We've simplified and speeded up the procedure a bit, but a bomb run with the BZA and Stuvi 5 would have looked something like the following. After setting the drop speed altitude, keep the target on the bomb line, that's the long vertical line with the aircraft level. Send to trim, press the drive brake button and set the engine to idle. Follow the target until it appears about halfway down the nose window. Close the radiators and set the propeller pitch to 100%. The dive angle should be about 50%. Note the approach of the bow tie or cravata bomb sight below the main sight. Hold the target on the line until you hear the drop altitude warning buzzer. Pull up so that the dive bombing marker, the bow tie, is superimposed on the target. Hold it there for a moment and press the bomb release. Press the dive brake button again and apply power. Open the radiator and turn for home and a breakfast of smoked herring, strudel and ersatz coffee. Let's run that again in close-up in case you missed it. Bomb gone. Don't forget to subscribe if you want to see more like this. Until next time, from Dieter and me, bye for now.